So, first of all, one small error in the okay here one first of all one small error which I would like to correct. My questions last week at the end was just to give you some right to have a thought process, is how this fiber brick gratings are fabric means in terms of what characteristic of the material, right, of this fiber allows you to make such gratings. Okay. What requires in the case of a grating structure which you talked about in case of an optical fiber is, if this is the core region, okay, if this is the okay a core, right, this is core and this is clade, right. What we talked, that we will induce some grating structure over here with a grating period lambda, right, right. Says now what happens, what are we inducing over here in terms of grating period, what, right, what makes it different in terms of refractive index etc., so that the light gets reflected back, isn't it? We understood as a distributed feedback, basically each of this, right, grating periods act as a reflector corresponding to the refractive index change between each of this, right, period, what I am talking about this, right. So, there is, right, reflection at every point, and if this reflections add up constructively, we end up with a, right, refracted one and the transmission ceases, right. It is very similar to something like a Fabry Parrot right interference approach. Okay. I will discuss about it later, but this is very simplified form, right. See, some part of light will get transmitted, some will get reflected at the interface, again it will get part of that reflected, something reflected, something transmitted. Why? Because there is a refractive index change within the core. Grating period has a refractive index, let us say n 1 and n 0 n 1 like this, if it has, okay, right, then this reflection is possible, Fresnel reflection, correct, that is what. Now, how to induce this refractive index change basically, correct, that is so we can induce, one way is to change the characteristics of the material, change the characteristics of this material. How to change? Selectively, correct, material characteristics in terms of change in the refractive index, right. How to induce change in the refractive index of the material, okay, that is one aspect, index. Second one, physically can we introduce a grating structure physically, okay. So, in case of a waveguide structure, we can also introduce physically right a grating structure. What it means physically means you really right, you really remove some material such that it produces let us say some air pocket, let us say with a refractive index n 0, then grating structure with refractive index n 1 n 0 n 1, right. I will show you physical what it means. So, first of all the core of this fiber, optical fiber generally is SiO2 plus germanium oxide, okay. These are the core materials, okay, and that gives us a refractive index n core, which is slightly different from n clade, which is, let us say, is SiO2, okay, slightly different. So, the core is having a refractive index n core, of course, we know already. Now, if we use a laser beam with a wavelength around 248 nanometer or so, which is krypton fluoride excimer laser we use. It interacts with this material SiO2 germanium oxide, it interacts, and the correspondingly it induces the material characteristics change because of this oxygen getting maybe detached physically because of the interaction of laser beam with this material, and this oxygen deficiency from this material ends up with a change in the refractive index of this. Okay. Slight refractive index change, core is let us say SiO2 plus Ge, right, germanium oxide, but after interacting with the laser beam, what happens, this oxygen gets detached or oxygen deficiency comes into picture. So, because of oxygen deficiency, so core interacting with laser beam, okay, of UV laser beam 248 nanometer or 193 nanometer. 248 nanometer is krypton fluoride laser, 193 nanometer is argon fluoride laser. If it interacts, oxygen deficiency comes into picture, and because of that what we will see is some material characteristic change. So, N core over here changes by small amount. Okay. So, N grating structure, N grating, that whatever wherever interaction takes place, that will be slightly different from N core. Okay. And this difference delta N is of the order of 10 raised to minus 3 to 10 raised to minus 5, small, very small change, refractive index change. Okay. Delta N refractive index change, but that is good enough. Now, the question is, how do you induce this refractive index change, periodical refractive index change? You should induce periodically, why periodically? Because the grating structure is, we observe that it is not very right, its separation, right, the grating period is very small, right. So, as to induce such change in the refractive index, and that too periodically, to induce this diffraction grating, we should use indirectly interference approach. When when two light beam interfere, they will produce intensity variation, isn't it, right. So, if laser beam interacts with another laser beam, right, with the same phase, right, then what you will see with the same wavelength polarization state, same and same phase, you will see that there will be intensity difference like this. Okay. Why intensity? Because of the interference coming into picture, constructive interference. Because of this, the intensity will be large at one point and very small at one, right, which will induce and if I tune this angle such a way that the interference pattern will produce, this will be with a grating period matching with what I want in a fiber brick grating, isn't it? I will be able to induce this, okay, refractive index change, because the intensity will be large at certain points. Wherever the intensity is large, the refractive index characteristics will change, material characteristics will change, and it will induce the grating period. Is it okay? So, this is the way we can fabricate. Of course, there is another method, phase mask approach, to produce such intensity variation. Okay. This is interference approach what I showed you. There is another approach to diffract the light beam and produce the intensity patterns also, and then generate such grating periods. Okay. It is possible, and so So, in order to fabricate such grating structure, we need such right lasers, we need some interference, right, such approach to generate this type of grating structure, etc. And that is what in the last class I think I was just trying to I think I just showed you that picture, I think so, I am not remember, this is right, I had shown you, and this I have picked up from right the reference science direct reference. I just to show you theta by mist, right, last time it was also to the Bragg sequence. So, this is the way we can generate the interference pattern and a grating structure. Okay. So, this, and what is the use of this fiber Bragg grating? One more thing I should tell you, just it's a very this whenever they want to fabricate such interference pattern, they should ensure that it should be ensured that it is fabricated on the core, correct, not the plate structure, core structure. So, sometimes we remove this, right, structure, this structure is removed and then fabricated. Okay. That is of course, it is a at the manufacturing level it is important, but now. So, fiber Bragg grating, as you can understand, allows part of the light, right, to be transmitted, right, while some wavelengths will get reflected. The wavelength which will get reflected is based on which it is decided based on this grating period. As we learned that this grating period where the wavelength is getting reflected, Bragg wavelength it is known as, is decided based on 2n and right grating period, right. N is of course average refractive index change, okay. Core refractive index plus small change, right, it is just an approximation, approximately 2n into grating period, and grating period is determines the Bragg wavelength. And now what is the use of this, right, fiber Bragg grating is we can make use of this type of structures to sense some right something to sense, right, basically what are the parameters that it can sense very easily, and which is of course you may think it is right, it is simple, is first one is temperature. It can easily sense the temperature, because if there is a temperature change surrounding this grating or fiber, what will happen, the grating period will change due to thermal expansion, right, or contraction, whatever temperature change will induce thermal expansion or contraction. Okay, that is one aspect. Secondly, the refractive index of the material will also will change by small amount. Okay. So, these two parameters influences the change in the Bragg wavelength, right, change in the Bragg wavelength, and that can be captured in this, right, with the help of fiber Bragg grating. So, if I can mount fiber Bragg grating on a tissue structure, I should be able to capture the change in the tissue temperature, is not it. So, in some of the applications such as for example, in hyperthermia means development of such systems where radio frequency induce heating of the tissue is taking place, and we want to capture even the temperature information when heating is taking place. We cannot put right other type of sensors so easily over there, because the problem is it will interfere with the right thing. So, as to take care of such aspects, what we do is we can make use of such fiber Bragg grating. There is no as such interference in terms of right electromagnetic wave, etc., and it can easily capture. And so, the change in due to the okay response to temperature, response to temperature is captured by via change in the Bragg wavelength, and the Bragg wavelength changes because of two effects. One is expansion coming into picture, right, expansion or contraction. So, right, so thermal expansion coming into picture, right, as well as change in the refractive index, right. So, change in refractive index coming into picture. Okay. So, this part is given by change in the Bragg wavelength. So, delta lambda b is the change in the Bragg wavelength, which is change in the Bragg wavelength, okay, is given by 2 n lambda to alpha. Alpha is nothing but the thermal expansion, coefficient of thermal expansion. Okay. Okay, plus okay. So, change in the room temperature into alpha into 2 n lambda will give you the expansion or contraction of the fiber Bragg grating, right, and this part will give you refractive index change, right. Okay. For glass means basically silica SiO2 material, refractive index is approximately 1.45. That refractive index, this temperature based on refractive index, no change is or sorry, basically the change in refractive index based with respect to the change in temperature, this value is approximately 1.1 into 10 raised to minus 5 per Kelvin. Okay, alpha, which is thermal expansion coefficient, is 5 into 10 raised to minus 5 per Kelvin. Okay, etc. Is it okay? So, this is the way that it can capture the information. Okay. And so, this is response to the temperature. It is also possible to capture the response due to the strain induced in the material, response due to the strain induced in the material, correct, strain induced in the material. So, we can also capture the material, let us say tissue is getting stressed or strained, okay, and if we can mount fiber Bragg grating on the top of it, when the tissue is getting stressed, then the fiber Bragg grating will also, right, accordingly get strained. So, the strain induced in the material can also change the refractive index. So, not only refractive index because of the photoelasticity coming into picture, but also changes the due to the strain induced, the material will get, right, stretched or compressed, right, that can also be captured. So, if we consider only the strain component, okay, let us say strain induced in the material is epsilon, then change in the Bragg wavelength is nothing but change into epsilon, is not it, into epsilon, if we consider only strain induced in the material. But if we consider the photoelastic components, okay, associated with the optical fiber itself, okay, whenever the fiber undergoes such strain, what happens, refractive index also gets affected accordingly, okay, which is basically connected with the photoelastic effect, of this, and that photoelastic effect if we consider. So, the photoelastic effect, this is strain effect, right, strain related, and this effect is associated in terms of this. Okay. So, this components P11 and P12 are photoelastic constants depending upon the direction of, right, orientation of the crystalline orientation, etc., a constant, and nu is Poisson's constant, right, Poisson's ratio, Poisson ratio. Okay. So, in case of silica, P11 is 0.121, P12 is 0.27, nu is approximately 0.17 at 1.5 micrometer. Okay. The wavelength is 1.5 micrometer at this. Okay. Epsilon is nothing but the strain. Strain is, as you know, it is defined as small change in the length with respect to the initial, right. That is okay. So, just the way sometimes the strain is expressed in terms of micro strain. What is the relationship between strain and micro strain? So, strain expressed in terms of micro strain. Oh my god. So, micro strain is basically strain into 10⁶, okay, micro strain. Yes. So, sometimes some text books, etc., they will express the micro strain induced in the material is so and so, it is very small amount, and strain is very small amount. So, the we are trying to express it in terms of some large number, right, in terms of micro strain, that is all. It is of course, micro means, right, corresponding to the 10⁶. So, actual strain induced is whatever number they have given in terms of micro strain divided by 10⁶. No, 10⁶. So, strain induced, actual strain is very small, is not it? Strain induced is whatever number is this micro strain divided by 10⁶, automatically it will give you small number, is not it? That is this, right. So, this micro strain number may be large, let us say 0.1, but actually strain induced is 0.1 into 10⁻⁻⁶, because this will go denominator. Okay. So, that this will give you, right, strain induced in the material, right, micro strain divided by 10⁶, correct, right. So, of course, this just to give you so that you will, right, remember, right, that is why. So, now fiber Bragg gratings. Now, another approach of using this fiber Bragg grating is we can use it in a distributed form. Okay. So, what it means, let us say it is a very large, okay, a grating fiber, optical fiber, long optical fiber with a core, okay, and we may induce, okay, we will induce one, let us say, grating structure over here with a grating period, let us say lambda 1 here, right. So, corresponding Bragg wavelength is lambda b 1, correct. Now, we can induce another grating period over here with grating period lambda 2 and correspondingly lambda b 2 as the grating, right, Bragg grating. Then similarly lambda 3, similarly right, it is possible. So, they are placed at different positions. Okay. Now, this type of structure is useful to capture the information about change in temperature at any of these points, is not it. If the tissue is having different temperature here, this Bragg wavelength will change, is not it, while the other wavelengths will not change if the temperature is not changing. So, indirectly I can capture temperature 1, I can capture temperature T 2 over here somewhere else, right. So, this is a distributed Bragg grating structure. Okay. Distributed Bragg grating structure allows us to capture the information from various positions, right, at different positions. So, of course, not related to biomedical, right, biophotonics, but it can be useful in some big large systems along the, let us say, conductor or in a boiler plant to measure the temperature at different positions, but using only one fiber. Light will transmit through broadband light source will pass through one fiber, and we will see the transmission characteristics. If there is no temperature change, what you will observe in the transmission characteristics is corresponding to each of these wavelengths, there may be a deep, right, in this spectral characteristics, right. So, this is the transmitted, let us say, spectra, transmitted spectra. Which is this is nothing but the right, maybe maybe intensity, maybe some, right, output from the detector, right, detector output, basically it is detector output in terms of maybe millivolt or volt, whatever, and this is the wavelength, right, part lambda b 1, lambda b 2, lambda b 3 we can capture, okay, as the deep, because this wavelengths due to the Bragg they will reflect back over here, is not it. So, the transmitted spectra of the input spectra is a broadband light source, right, broadband light source input spectra, is not it. The transmitted spectra has deeps associated with the Bragg wavelengths. Now, if any one of this wavelength gets changed, why? Because of the temperature change or because of the strain induced, etc. What we will see a small, if wavelength changes, this deep will, right, will shift over here, let us say, other dips remains the same, right. So, wherever there is a shift in dip, there is some characteristic of the material has changed. Of course, you will not be able to distinguish whether temperature induced or strain induced, okay, that you may not be able to distinguish, right, because both will induce some wavelength change, okay. But you will have something fixed as a parameter and then try to capture the other information, but it is possible to use this way, is it okay. So, this fiber Bragg grating also allows distributed such measurements, okay. And now, a little bit towards, let us say, biomedical, how can we make use of this with biomedical. So, as I told you that, let us say, okay, this is okay, maybe let us say this is our fiber Bragg grating, okay. Okay, over here, correct, this is the fiber Bragg grating, and now of course Okay. So, in case of biological tissues etc., this grating structure is mounted on right biological tissue. Okay. So, the tissue structure may be right will be here, okay, etc., and it is mounted. So, there will be some bonding coming into picture as well. Okay. Bonding is required, okay, between optical fiber and this tissue structure. Okay. So, there will be some bonding coupled with it, and then the light transmission will allow in case of a tissue structure. Okay. So, this is the way Bragg grating structures are used for such purposes. Now, related to optical fiber, I am going to another aspect related to the optical fibers only. It is holy fiber or okay, photonic crystal, right, fiber. Okay. So, there are two types of photonic crystal fiber. They are different, the optical fiber characteristics are slightly different, and there are two types of optical photonic right crystal fiber. One is based on total internal reflection, and the second one is based on right holy fiber or hollow core, okay, hollow core, right, holy fiber with hole. So, basically it is known as holy fiber. Okay. So, in this type of this so the fiber has let us say a buffer layer, and core part has within this core which is of the order of let us say in terms of dimensions, it is of the order of 125 micrometer, okay, of the order of okay micrometer. So, within this it has periodically spaced some right holes, okay, such that this is of course high refractive index core. Okay. So, this is high refractive index core material, but within this there are holes with certain periodical right, periodicity. Okay. Some pitch P is there, okay, with this they have placed. Now, the center portion is solid, okay, it is solid. So, they have the same material, it is same high refractive index core only, but center portion is solid, not periodical hole. So, this approach allows light to remain confined, okay, some part of the light remains confined in the core with a high refractive index. The surrounding region also has a high refractive index, same material, however, it is with the holes. So, it is basically functionally graded material, it is indirectly functionally graded. So, the resultant refractive index is slightly different, okay, because of this holes periodically this whole structure, the refractive index right resultant of this solid core is slightly different from the central solid core portion. Is it okay? So, the light remains confined to this. However, because of this type of characteristics, this even we can couple some part of the, let us say in case of an optical fiber, I want to use one light beam which is acting as a pump source, and the material, center material is a gain medium. Okay. We will understand about these terms when we talk about light sources. So, they are gain medium. So, this pump is exciting the gain medium, and we pump intensity is large. So, I cannot couple in a very small core, I cannot couple the whole light intensity, because the intensity is so large, pump intensity, it should not damage the core. Okay. So, what is done? The pump beam is coupled with the larger diameter core, while the gain medium is constrained within a small region where the interaction is intense. So, the light, when pump light, when propagating through this core, overall core, will interact with the gain medium effectively. Okay. So, this is one approach wherein the light will remain confined, which what the light travelling through this solid core will remain confined. However, the nearby region has a slightly different refractive index, such that it allows the light to remain in this core and transmit, right, and also means allows the transmission, not like clade. Clade will not allow the light transmission, is not it? It will only allow the light to transmit through the core, but here this region surrounded by this solid core can also allow the light transmission, and this is photonic crystal fiber is it is designed, right, and this there are various parameters. One of them is the this hole size and hole pitch. They will determine the amount of light which can be confined to this, right, region. And the other way round to this type of photonic crystal fiber is another, right, hollow core is hollow with a hole, okay, not the solid like this. So, the configuration almost, right, remains the same as it is described here, but okay, but the center part is hollow, okay, it is hollow, okay, center portion is hollow. It is hollow, okay, or with hole, okay. Now, this geometry of this type of photonic crystal fiber with functionally graded configuration such as like this, okay, with solid this buffer, okay, high refractive index core, okay, high refractive index, right, material, and hollow this core allows, okay, this geometry with certain design allows the light to travel through this hollow core, although the refractive index is lesser, is not it, as compared to the surrounding solid core, but light will remain confined due to this geometry with photonic crystal, this fiber, this geometry. The light will remain, light will be confined within the hole, okay, within this core region, light will remain confined, while travelling, propagating through this fiber will remain confined in the core, right, hollow core region, okay. So, that is one, but manufacturing etcetera is quite challenging, right. How to manufacture such optical fibers with hollow cores or with such functionally graded right, material characteristics etc. Oh my god, 10:56, we will stop here.